Ladies and gentlemen, welcome to my presentation, Hydrogen, the Miracle Substance for the Decarbonization of our Energy System. This is an online lecture which I will give now, which will last a little bit more than 1.5 hours. And this lecture belongs to the series of lectures Energy Transition, which is held at our university. It is recorded on October 18th of 2021. And a few days later, it will be put on YouTube so that you can watch it at YouTube at any time when you want. And there will be an online discussion on this presentation on November 9th, 2021 in the afternoon at 4:30 Central European Time, which is UTC +1. The access details for the online discussion will be shown on November 9th on our website www.hshl.de. My name is Prof Goebel. I am a professor at this university since 9 years. Few words on my CV. So I studied mechanical engineering at the University of Aachen, RWTH Aachen, and graduated in mechanical engineering. And my first job was with the European Space Agency, ESA. And there I spent only 1 year, and then I moved to the German Aerospace Center, DLR, where I stayed 9 years. But there I didn't work on space technology. There I worked on solar technology because the DLR is one of the leading energy research organizations of Germany. And there I focused on solar thermal power plants. Then I made a PhD there as a side occupation at the Technical University of Munich. And after 9 years, I left the DLR and went to a small project developer called NEWAG in the town of Wiesbaden in Germany. And then I went to the company Lammeyer, which is one of the big internationally active engineering consulting companies. This company named Lammeyer now belongs to the Tractebel Group. There I was, as I said, 6 years. I started as an expert for solar thermal power plants, and later I became the head of the department for renewable energies. And my last job before I became a professor 9 years ago was in Abu Dhabi. There I joined the Masdar initiatives. Those of you who don't know Masdar, please look it up at www.masdar.ae. AE like Arab Emirates. It's a fantastic organization for the promotion and implementation of renewable energies. And there I worked in the business unit Master Power, where I was the head of engineering for 5 years. And in that function also I managed the project Shams 1, which was the largest solar power plant of its time there. It's a 100 megawatt parabolic trough power plant, which is operational since also 9 years now. And after this time, 5 years in Abu Dhabi, I returned to Germany with my family and I became a professor because in all the jobs where I worked before, I faced a scarcity of engineers. Engineers are really hard to get, and so I thought I will contribute to the education of engineers, and so that's what I'm doing. Since 9 years, I'm educating engineers. All right, so to the content of this speech. First, we will see the energy transition requires storage. We will look at different types of energy storages. We will look at hydrogen as an energy carrier. We will look at the properties of hydrogen, the production of hydrogen, the utilization of hydrogen, road transport, the role of hydrogen in the energy transition, and the conclusion. And one important thing, so I have translated this lecture from German into English because there was a request from my international friends that they would like to hear this lecture in English. So I did the translation and I will hold this lecture here in English. But however, the figures still refer to Germany only. That means all the economic and technical figures. I use here Germany as an example country. So if you want to have similar things for your own country, unfortunately, you have to dig out those data yourself. All right, so let's get started. So the energy transition requires storage. So let's look at the net electricity generation in Germany in the year 2019. So there was 513 terawatt hours was the net electricity generation, and almost 50% of this 46% here, came from renewable. And the largest share here came from wind, then biomass, photovoltaic, and hydropower. And the remaining electricity generation was from natural gas, from nuclear, from lignite, and from hard coal. So looking at the renewables, electricity generation from biomass is dispatchable. Hydropower is partially dispatchable, so you have one of the river plants which are not dispatchable, but those with storage lakes, they are dispatchable. So unfortunately, electricity generating from wind and solar is fluctuating. And unfortunately, only wind and solar have further potential in Germany. Hydropower and biomass don't have any further potential because there is no additional area available, neither for biomass nor for hydropower. So let's look at the different sectors of energy. So we have the electricity generation. So we have of the gross electricity generation, we have 41% renewables. The traffic sector is 5.6 renewables, stagnating. And the electricity generation is increasing every year, the percentage. Traffic sector is stagnating at 5.5%, and the heat sector is stagnating at 15%. So here you see over the time from 1919 in the last 30 years how the electricity sector really picked up speed and is continuing to grow. In the year 2020, we already passed the 50% line with the renewable electricity generation in Germany. But as you see here, traffic and heat sector are stagnating. So, and electricity is not everything. Only approximately 1/4 of the primary energy consumption goes into electricity generation. So let's look at the primary energy consumption of Germany. So here the renewables are not as big as they were in the electricity generation only. So if you look at the complete primary energy consumption of Germany, there were only 14% renewables, and the biggest share was oil, then natural gas, hard coal, lignite, nuclear. And within the renewables, there was biomass was the biggest, which is biomass for heating systems. So that means it's also including the wood firing. Then, and here is the electric, which is wind, hydropower, photovoltaic, and photovoltaic. And as I said before, unfortunately, only wind and solar have further potential in Germany. And because these are not dispatchable and they are fluctuating, we need energy storage. So energy storage is a must if we want to increase the share of wind and photovoltaic to significant percentages. So let's have a look at some energy storages. Because I always notice, very often I notice that people really have a little bit problems understanding what an energy storage is. A very simple energy storage is this with a little toy where you have to wind up a spring and then this toy is operating for a few seconds. So this spring energy storage stores an energy of approximately 10 watt seconds, which is not a lot. Then these typical batteries, rechargeable batteries, which we all know. In this example, it has 1.2 volt, 1.3 ampere hours. It has 1.5 watt hours. But be careful when you compare this. This were watt seconds, and this is a watt hour. So 1 watt hour is 3,600 watt seconds. So in the end, this battery has 500 times more energy than this spring. I think this is pretty obvious because when you wind up such a toy, it runs for 10 seconds, and with a good battery, such a toy could really run for more than an hour. So this is why it has 500 times more energy than the spring. Let's look into the next bigger system, a starter battery for a car. I think we still all know this system. These are the batteries which are used to starting our cars. This, for example, has 12 volt and 50 ampere hours. And volt times ampere is watt. So that means the energy content of this battery is 600 watt hours or 0.6 kilowatt hours. And this is again 384 times more than this battery. Next step is we look into a fuel tank of this motorbike. Of course, the output of fuel is not directly electricity, but it is an energy storage. So, and this tank fits 10 liters, and the energy content of 1 liter of fuel is approximately 10 kilowatt hours, 1 liter. And when we have 10 liters, we have 100 kilowatt hours in this tank. And let's look back to the battery. The battery had less than 1 kilowatt hours. That means we have 160 times the energy of this starter battery. We have it here in this tank. This shows, I think, pretty clear why electric driving with lead acid batteries, like shown here, is not really an option. Imagine with 160 of these batteries, this motorbike would break together and couldn't run. By the way, if you go back to the spring, this is 36 million times the energy of the spring. But as I said before, the output of the fuel is not directly electricity. We have to convert it in an engine to mechanical work, and then we get only 1/3 out of this energy we can convert into moving mechanical energy. And by the way, when we have electricity, the efficiency of electric motors is very high. It is above 95%. So let's look into a more modern system, power system. Electricity storage system. This is the Tesla Powerwall. The Tesla Powerwall shown here, we see actually 2 units at the wall in a garage, has 13.5 kilowatt hours. So this is 22.5 times the lead acid battery here. But compared with the motorbike tank, it is only 13% of the motorbike tank. So that means for a battery, this is a pretty good system. So it is 20 times more than this battery. Compared to a fuel tank, it is still not very good. What are the costs of this? Such a lead acid battery, or this is not converted into English, sorry, this is a lead acid battery, is 60 euro per 0.6 kilowatt hour. So it is approximately 100 euro per kilowatt hour. A Tesla Powerwall, I just looked it up in April this year, costs 9,600 euros for 13.5 kilowatt hours. So it is 711 euros for kilowatt hour. Little explanation here. Sometimes when I mention these numbers, I look into phases where I see some confusion and people tell me, if I pay for my electricity, the price on my electricity bill is something like 20 or 30 euro cents per kilowatt hour. So why are we talking here about 100 euros per kilowatt hour or even 700 euros per kilowatt hour? And the explanation is, look, here we look into a battery, which is a vessel which can store electricity. So you can compare this with water. When you pay water from your utility, you pay much less than 1 cent per liter. But when you buy a water storage, you pay also several euros for this storage. Let's say you buy a bucket, a 10-liter bucket. You might pay 5 euros for this. But the 10 liters of water which you will put in there is only 1 cent. And the same is here with the electricity. The electricity, yes, you can buy it for 20 or 30 cents per kilowatt hour. But this is a storage vehicle which can contain 1 kilowatt hour, or in this case, 0.6 kilowatt hours. So this is why the prices for this are high. This is not the price for electricity. It is the price for the storage. And now let's get even bigger. A pumped storage power plant. The biggest in Germany is near the town of Goldistal. Here you see 2 lakes, a lower lake and an upper lake. The volume is 12 million cubic meters. The height difference is 350 meters. And the power you can get out with the powerhouse here is 1 gigawatt. And the energy is 8.5 gigawatt hours. That means you can run this plant for 8.5 hours with 1 gigawatt, and then all the water has run down and the storage is empty. But this is a lot of energy. This is 630,000 times the energy of the Tesla Powerwall. And also let's look at the prices here. The pumped storage power plant in Goldistal costed 600 million euros for 8.5 gigawatt hours, which is 8.5 million kilowatt hours. So the price per kilowatt hour is 73 euros per kilowatt hour in this plant. So you see this is 10 times cheaper than a Tesla Powerwall. And that means the utilities who have the chance to build such plants, of course, prefer to build this. But we will learn later during the lecture, there is not much land available for more plants like this, at least not in Central Europe, maybe in Russia or in North America or in other continents, but in Central Europe, these places where this is possible is very rare. So it is cheap where it is possible, but when it is not possible, we have to go for other solutions. Yeah, let's look at pumped storage in Germany. So the only storage technology available in noteworthy scale in Germany until today are pumped storage power units. We have an installed capacity, if you look at the power, of 6.5 gigawatt. Now we need to look at one important number. The average power demand of Germany is 70 gigawatt. So on the average means average, right? 70 gigawatt is our average power demand. That means on very cold days, we need, when heating is running, so we need sometimes 90 or 95 gigawatts. And in low demand times, that means in the summer, in the evenings, maybe it is 30 gigawatt. So that means low demand is 30 gigawatt, high demand is 90 gigawatt. The average is 70. Our pumped storage plants have a capacity of 6.5 gigawatts, so approximately 10% of our average power demand, which is quite significant. The installed capacity is 33 gigawatt hours. That means those plants can run approximately 5 hours at full power and then they are empty. And compare this with stationary battery capacity in Germany, which was in the year 2018 was 1 gigawatt hour. It is increasing with all the Tesla Powerwalls and other solar storages, but it is still below 2 gigawatt even today. But in electric cars in the year 2020, it was already 15 gigawatt hours. That means in the electric cars, it is coming into the same range like the pumped storage. And this is important, and then we will come back to this in a minute. So the installed capacity of 33 gigawatt hours can provide the average power demand of Germany for half an hour. It means this is not really a seasonal backup. It can help us if all fossil-fired plants get lost. We have half an hour of energy in our pumped storage plants. So this capacity will soon not be sufficient anymore for compensating the increasing share of fluctuating generation from solar and wind. Here is a footnote here on the electric cars. We had last year 300,000 electric cars, each of them 50 kilowatt hours. So that brings us to 15 gigawatt hours. And if all 40 million passenger cars in Germany would be electric cars, again with 50 kilowatt hours storage, which very soon will be more than this, but let's be realistic or pessimistic. So if all 40 million cars will be electric cars with 50 kilowatt hours each, we have 2000 gigawatt hours of battery storage, which then will be much more than the pumped storage is today. So with this amount of energy, we could run Germany approximately 30 hours. You see, we have 70 gigawatt average demand. And if you run this for 30 hours, 70 times 30 is 2,100. So we can run 30 hours more than a day than on the electric cars if they would be available for the grid. So now let's look into hydrogen as a storage. When applying an electric voltage in water, oxygen is collected at the anode and hydrogen at the cathode. The respective device is called an electrolyzer. So here you have an electrolyzer, here you have water plus minus, and here you can collect oxygen, and on this side you can collect the hydrogen. This process can also be reversed. In that case, hydrogen reacts with oxygen, resulting in water, while electricity is generated. The respective device is called fuel cell. Hence, the energy of electricity can be stored in hydrogen and later can be reconverted into electricity again. This is why hydrogen is a storage option. In large scale, the conversion from hydrogen to electricity will rather happen in gas turbine plants than in fuel cells. It is cheaper in large scale. So we don't need to wait until we will have fuel cells in the gigawatt scale, because when we have large amounts of hydrogen and we want to convert them into electricity, we can easily do that in gas-fired power plants and with an efficiency of 60%, which is the same efficiency like fuel cells. So this is a cheap and realistic option. So let's look at strengths and weaknesses of hydrogen as a storage. One big strength is the following. When you want to double the capacity of a battery, you either need 2 batteries or 1 battery of the double size. The double battery has also a double price. Hence, a storage for a month is 30 times as expensive as a storage for a day. This is different with pumped storage and with hydrogen storage. Here you don't need to increase the capacity of the inverter, but only the capacity which stores the energy storing medium, which is hydrogen or water. So at a pumped storage power plant, the pump and the turbines stay unchanged if you want to increase the capacity. Only the water pools need to be enlarged, and they are not the most expensive part of the plant. So this is why, as I said, with batteries, you want double the size, you need 2 batteries. You want 30 times the size, you need 30 batteries. And with the pumped storage, you can keep the pump, you can keep the turbine, you only need bigger pools. And with hydrogen, so the electrolyzer and the fuel cell or gas turbine stays unchanged. Only the hydrogen tank needs to be enlarged. So let's look at the system again. We have electricity, goes through an electrolyzer, we receive hydrogen, we store it, then we take out the hydrogen, put it through a fuel cell, and we have electricity. And now we want to double the capacity, and we only need to increase the storage. And the electrolyzer and fuel cell stays the same. This is why this is so much cheaper for long-term storage, while batteries are not affordable for this. Now comes the disadvantage, the round trip efficiency. Let's look at first into liquid hydrogen, which is displayed as LH2, liquid hydrogen. So we have a starting point, we have an electric energy of 100 kilowatt hours. We put this through a very good electrolysis with 75%, and then we have from the 100 kilowatt hours, we keep 75 kilowatt hours, and that is a mass of 2.25 kilogram of hydrogen. Then comes a liquefaction, and we need to liquefy this. We need 22.5 kilowatt hours electric, and because approximately for liquefaction we need 10 kilowatt hours per kilogram. Because we have 2.25 kilogram, we need 22.5 kilowatt hours electric. Then we have 75 kilowatt hours in liquid hydrogen. So then we want to reconvert it into electricity. We put this through a fuel cell or through a combined cycle gas turbine with an efficiency of 60%, which is state of the art, and then 60% of 75 kilowatt hours are 45 kilowatt hours electric. So then we have 45 kilowatt hours. Now let's look at the round trip efficiency. The round trip efficiency from electricity to electricity is 45, what we have afterwards. But our input was not only 100 kilowatt hours for the electrolyzer, we had another 22.5 kilowatt hours for the liquefaction. So our round trip efficiency is 45, what we get out when we reconvert it, divided by 122.5, which was our input. So the round trip efficiency from electricity to electricity is 36.7%. Hence, it is significantly worse than pumped storage. Pumped storage has 75%, or compressed air storage, which we will look at in a second also, has 70%. So that means we have a lower efficiency than those competing technologies. Now we looked into liquid hydrogen. Now let's look into pressurized hydrogen. And this calculation is pretty similar. We have a starting point of electric energy, 100 kilowatt hours. Then we have an electrolyzer, and then we have the same like before, 75 kilowatt hours. And now we compress it to 200 bar. And to compress hydrogen from 1 bar to 200 bar, we need approximately 3 kilowatt hours per kilogram. That means in total 6.75 additional electricity. So then we have compressed hydrogen, and then we reconvert it into electricity like before, and then we receive 45 kilowatt hours electric. And now the round trip efficiency is better because we still get out 45, but our input is lower. Our input was 100 kilowatt hours plus 6.75, and so the round trip efficiency is 42%. But it is still significantly worse than a pumped storage or compressed air storage. So let's look at the general properties of an energy storage system. The three most important properties of an energy storage are the following. First, power. So with which power, measured in kilowatt, we can charge and or discharge our storage. Then energy storage capacity. How much energy, how many kilowatt hours can we store in our storage? And then the round trip efficiency. It describes how much of the original energy is still available after the storage cycle. That means into the storage and out of the storage. With some technologies, the first two properties are connected with each other. For example, with batteries. That means when you have a higher power, usually you also have higher storage capacity. With other technologies, this is not connected, as we saw before, pumped storage or hydrogen. That means here, with the pumped storage or hydrogen, we can increase the storage capacity without touching the power. And this is why we can increase the storage capacity at very low cost. While with batteries, a bigger storage capacity brings us, if we want it or not, also an additional power. And then this makes it more expensive. And this is so expensive that batteries will not be used as a seasonal storage, where they are only charged and discharged once per year. So other further important properties of energy storage systems are the cost, of course, power specific. So how much euro per kilowatt of charge or discharge power. The cost of energy, that means capacity specific, euros per kilowatt hour of storage capacity. Then, of course, the working lifetime. There are two parameters. One is the lifetime in years, and the cycle durability. How many cycles can the battery survive? Then, which is especially important for transportation systems, so the storage capacity mass specific. So how much energy can we store per kilogram of battery or storage system? And then volume specific, kilowatt hours per liter of battery volume. So these two are especially relevant for transportation systems, so in cars and trucks. The ratio of energy storage capacity to power determines the application as a short or long-time storage. The following list shows different storage technologies sorted according to their duration in an ascending order. So a few seconds we have electric condensers. Then we have a flywheel electric batteries, pressurized air, pumped storage, power to gas, which power to gas can store energy for several weeks or even months. So the table below summarizes some storage technologies with the essential properties. So let's look at the pumped storage. Has a round-trip efficiency between 70 and 80%. The lifetime is very long, 50 years plus. The price per kilowatt is around 1200 and the price per kilowatt hour can be as low as 20. But here you see the footnote 1, the costs are strongly dependent on the local geographic conditions. For example, existing lakes. The first pumped storage plant of the world was built in Bavaria in 1924. It had 2 natural lakes where they only had to build the turbine and the pumps and the pipes. Of course, in such a system, it can be pretty cheap. In some other places, you have to build one of the reservoirs, and that makes the system expensive, and this is why the cost here is higher than 20. But 20 are those plants with very good boundary conditions. So remark is this is definitely state of the art. Pressurized air has, when it's done in an adiabatic way, a 75% efficiency, which is pretty good. Lifetime is also pretty high. The cost per kilowatt are comparable to pumped storage. The price per energy is much definitely higher. There are prototypes, but they are not yet state of the art. Then let's look at power to gas, hydrogen. This you call power to gas because you take the electricity, produce it into gas, and then you reconvert it into electricity. So the round trip efficiency here is around 40%. The lifetime of the components can be assumed with 15 years. The price per kilowatt is in the range of 2,000 euros per kilowatt, and per energy storage, it can be also pretty good, as we learned before, when you store really for a very long time. And then that means the electrolyzer is running 4,000 hours per year, and then for another 4,000 hours you are reconverting it per year into electricity. Then you can reach pretty low energy specific costs. It is a pretty complex system, and this is and yeah, it is a state of the art, but it hasn't been built in very large quantities, different than pump storages, which are available since more than 100 years. And then you can go even a step further because hydrogen is not so easy to store, as we will learn in a second. You can convert it into methane, and then you can store it easier, but then the round trip efficiency is even lower than 30%. That makes also the cost more, the costs are higher. Then let's look at lithium ion batteries. The round trip efficiency is a little bit better than 90%. Lifetime 10 to 16 years, of course, depending on the number of cycles. And the cost per kilowatt is between 200 and 400 euros per kilowatt, and per kilowatt hour the price is also 200 to 400 euros per kilowatt hour. This is the system price. The pure batteries, you get them already below 200 euros per kilowatt hour. But when you, like the Tesla Powerwall, when you buy a system, that means which with a charge controller and a discharge controller, then the system prices are well above 200 euros per kilowatt hour. But they are state of the art, and their price continues to go down. Any other footnotes which we didn't look at it? So footnote number 1, the costs are strongly dependent on local geographic conditions, as we discussed before. Footnote number 2, here with the batteries, when you have 100 charging cycles per year, that means every second or every third day you can charge your car, then it will have a lifetime of 10 or 16 years. And then the battery is not dead. It is only defined, then usually you define the end of the life when the capacity goes below 80% of the original one. But of course, it is still working. And here, the energy specific costs are strongly dependent on the storage duration. That means high energy and low power is lower cost per kilowatt hour. That means those numbers here are for annual, for a seasonal storage, not for a daily storage. And number 5 here, this number is valid for battery electric vehicles, standardized and large quantities. And the potential for future pumped storage or pressurized air storage in Germany is limited due to geographic reasons. And I think the same is true for all of Central Europe. That means this is nice to have, but it will not be a large player in the future energy system. It is a low-hanging fruit which you should harvest, but it cannot be extended much more. So these are the future systems: hydrogen, lithium-ion batteries, maybe future batteries which are coming up soon. There is a lot of research going on now. Or we have the power to gas with the methane conversion. The next picture here shows pictures here the different energy systems. Here we have the energy capacity in kilowatt hours. You see 1 kilowatt hour to 1 megawatt hour, gigawatt hour, terawatt hour. And here you have the discharge time. So as I said before, the very small systems are capacitors, flywheels, batteries. Then we have compressed air storage, pumped storage, and the real long-time stuff is power to gas with hydrogen or power to gas with methanization. Yeah, but now let's look into hydrogen itself. So this was a little bit quick opener into what we can do with hydrogen, but we now look, because hydrogen is the main topic of our today's lecture. So why is hydrogen an interesting energy carrier? Because the lower heating value of hydrogen is almost 3 times higher than the one of oil, mass specific. So the lower heating value of hydrogen is 120 megajoule per kilogram. The lower heating value of oil is 42 megajoule per kilogram. So therefore, it is particularly interesting for fuels, for vehicles, because the energy density of hydrogen is higher than the one of oil. However, at the end, this advantage is overcompensated by the very heavy tanks needed for pressurized storage. This we will also see later. Very big difference between hydrogen and oil or gas. Different than oil or natural gas, hydrogen does not occur in nature, at least not at free hydrogen, only bonded, for example, like in water, which is H2O. And hydrogen can be produced with 2 different methods. Out of hydrocarbons using suitable chemical reactions. Usually you do this with natural gas. Or out of water using electrolyzers, and which we learned before. However, the share of worldwide hydrogen production with electrolyzers is less than 5%. The majority is still produced with hydrocarbons. At some chemical processes, hydrogen is generated as a byproduct. For example, the coking process, where when hard coal is converted into coke, there is hydrogen is a byproduct, which you of course should catch and use. So it is important to note that hydrogen is not an energy source like oil and gas, which you find ready to use in the nature. It is an energy carrier, which you have to produce from another energy source. So summary of relevant properties of hydrogen. The atomic weight of H2 is approximately 2. The gas constant is 4124. The boiling temperature is in Celsius minus 252.8 Celsius or 20.35 Kelvin. So it's very low. The melting temperature, or when you come from warmer temperature, the freezing temperature is 13.95 Kelvin. The density at 0 degrees Celsius and normal atmospheric pressure is 0.09 kilograms per cubic meter, which is 14 times lighter than air. This is why the Zeppelins or the airships have been flying with hydrogen. The density in the liquid state is 70 kilograms per cubic meter, which is 14 times lighter than water. So it is a very low density liquid. The heating value is 120 megajoule per kilogram, or the unit which we use even more often in the energy business is kilowatt hours. So you divide this by 3.6 and then you have 33.33 kilowatt hours per kilogram, lower heating value. And when you have the volume specific heating value, then it is 3 kilowatt hours per norm cubic meter or standard or normal cubic meter. So this N is not a Newton cubic meter, it is a normal cubic meter. And the normal cubic meter is the volume at ISO standard conditions. That means 15 degrees Celsius and normal atmospheric pressure. Here it is written. And the volumetric heating value in the liquid state is 2.36 kilowatt hours per liter. So you see it is approximately 1,000 times denser than gas, which is not compressed. So due to the fact that the volume specific low heating value is 787 times higher than the liquid state, than the gaseous state, liquid hydrogen is used as a fuel in spaceflight. So in spaceflight, you use the fact that it is almost 1,000 times higher density. This is why you fill up the tanks of rockets with liquid hydrogen. Liquid hydrogen is abbreviated as LH2. Alternative is high pressure storage, and the common pressure ranges are 200 bar, 350. This is for transport. This is in tanks of trucks and buses, and this is in tanks of passenger cars. This has been established as a normal pressure. So what is the role of hydrogen during the energy transition? The energy transition means the move from the carbon-based system to a renewable energy-based system. As shown above, hydrogen is an energy storage and cannot score in all categories due to its low round-trip efficiency. However, the energy economy will have to use hydrogen as an energy carrier in the future for the following reasons. Batteries do have a much better round-trip efficiency, but at very large capacities, they are capacity-specific more expensive than hydrogen. That means batteries are not suited as a seasonal storage. A seasonal storage is a storage which you charge up once per year and discharge once per year. For example, with all the solar energy, which has a big surplus in summer, you put all this surplus energy into this storage. And then in winter, when the sun is not shining, you discharge this storage. And a battery, which you only charge once a year, is too expensive because you have to charge, when the battery has a lifetime maybe of maximum 20 years, this battery is working only 20 times. And the high investments needs to be paid on the kilowatt hour, which is stored there. So that doesn't work, and this is why hydrogen is the only suitable seasonal storage. Pumped and compressed air storages are only an option under special geographic conditions, which are not met everywhere. One of the best countries for this is Norway, with a lot of water and a lot of mountains. Also Austria and Switzerland are pretty good, the Rocky Mountain area in the United States. But there are many, many places where pumped storage doesn't work. So, and due to the fact that in Central Europe, the dominant renewable energies, PV and wind, are highly fluctuant, there will be more and more electricity surplus during the summer when the REN installations rate will increase, which they are doing now. This surplus can be used for long-term storage, seasonal storage. The surplus electricity will be cheap. Therefore, the low efficiency of hydrogen does not hurt as much as it seems at the first sight. So let's continue the role of hydrogen in the energy transition. There will be a certain order in the utilization of surplus electricity. So when we continue to build PV and wind, will have more often surplus electricity. What can we or what shall we do with it? So first is demand side management. So it means we need to incentivize the electricity utilization in times of surplus, and we have to penalize it. So it's penalize it in times of scarcity. This way you make sure that when there is cheap electricity on the market, people will buy this cheap electricity. And when the electricity is scarce, then you make it expensive, so the demand will go down. This is the easiest way of using the surplus. But of course, you cannot use it, you cannot manage all the surplus with it. So the next one is charging of batteries. If all 40 million passenger cars in Germany will be battery electric vehicles with 50 kilowatt capacity each, then the total battery capacity will be 2000 gigawatt hours, which represents 28.5 full load hours of the total Germany electricity consumption. So that is for the daily loops. Then we have power to gas, hydrogen generation by electrolysis. That means when demand side management has been applied and there is still a surplus, then you charge the batteries. When there is still a surplus, then you use the surplus electricity to produce hydrogen with electrolyzers. Or you can use electric energy for heating. We will come to this later, so I don't talk about it now. And the order here, what comes first, power to gas or power to heat, is discussable, and we will discuss that later during this presentation. Now comes an important thing, the hydrogen generation costs. The abbreviation here is HGC, hydrogen generation cost. The hydrogen generation costs consist of three components: capital cost of the electrolyzer and the complete plant, also the compressors and stuff, so which is called capex. Then we have the cost for operation and maintenance, also very often abbreviated with O&M, called the OPEX, and the cost of electricity, which we need for the electrolysis. The electricity cost. These are the three components. So the capex is distributed over the depreciation period by using the annuity method. So that means the interest and payback in constant rates over the lifetime of the components. The OPEX will be assumed as 2% of the capex per year. This is the typical value for this kind of infrastructure by experience. The biggest bandwidth exists with the electricity generation cost, because here we can assume really low values or high values. So we will just start with an example, and later we will discuss these numbers, which are realistic and which should be used, because that is not so easy. So let's start and make some assumptions. So the capex of the complete electrolyzer, the complete plant in large scale, this is not the home-based stuff, this is an industrial electrolyzer, costs 1,000 euro per kilowatt capacity. And with an efficiency of 70%, this produces a certain amount of kilogram of hydrogen per hour. And this is also a very common way of displaying the price. This is so 100,000 euros per kilowatt is 48,000 euros per kilogram per second capacity. The OPEX, as I said before, 2% of the capex per year. This is a non-variable OPEX. And the electricity cost, we take an example of 4 cents per kilowatt hour, because this is the average value, was in the last year the average value at the European Electricity Exchange. It was not in the last year, it was in 2020 due to Corona pandemic. It was very low last year. This is the average of the years before 2019. So we take this as an example. Then we start with full load hours, 4,000 hours per year. And we have some finance parameters. So we say we have a return on equity of our project 12%, a debt rate 4%, a debt equity ratio of 80-20. That means we have a weighted average cost of capital. So with these numbers, we have the weighted average cost of capital, so-called WACC, of 5.6%. And we have a depreciation period of 20 years. And then when we feed this into the annuity equation, we have an annuity of 8.44% per year. So that means our annual capital costs, they are 4,050 euros per kilogram per hour per year. So this is obtained by when we multiply this 48,000 here with the annuity. That means we have to pay 4,000 euros per year for each plant capacity of 1 kilogram per hour. And when the plant is running 4,000 hours per year, then the capital cost per produced kilogram is approximately 1 euro per kilogram is the capital cost. Then we have the OPEX. The OPEX here is 960 euros per kilogram per hour. This is obtained from this 48,000 times 2%. So this 48,000, which we had here, times 2% per year, is we have to pay 960 euros per year for the capacity of 1 kilogram per hour. And if we run this plant 4,000 hours per year, the O&M costs per produced kilogram are 24 euro cents. And then, so we summarize the total hydrogen generation cost here. This is still a W from the German word Wasserstoff for hydrogen, sorry. So hydrogen generation cost is the CAPEX, which we calculated here, the OPEX, which we calculated here, and here we have the electricity cost. At our system efficiency of 70%, we need 48 kilowatt hours of electricity for 1 kilogram of hydrogen, and each kilowatt hour costs us 4 cents, as we fixed here in our example. Here we fixed this. So on 4 times 48 is 192 cents, or 1 euro 92 cents. This is our electricity cost. And now we add up all the stuff. So the CAPEX plus OPEX plus the electricity cost together is 3 euro and 17 cents per kilogram of hydrogen in our example. So I copy the last line to start the discussion of the hydrogen generation cost. So is that expensive or not? Let's compare it with other stuff. So hydrogen produced from natural gas with the so-called steam reforming is 1.5 euros per kilogram. And now we convert this to energy. When we remember that the energy content of 1 kilogram was 33.3 kilowatt hours, we can convert this price here into a kilowatt hour price, and this is 9.5 cents per kilowatt hour. The hydrogen produced from natural gas here then is 4.5 cents per kilowatt hour, so a little bit less than half. But now let's compare it with other fuels. For example, diesel fuel. Diesel fuel was in the beginning of the year here in Germany, now it is even more expensive, 1.20 euro per liter. Energy technology engineers know that 1 liter of diesel fuel has an energy content of 10 kilowatt hours. So that means this diesel price per liter is 12 cents per kilowatt hour. So this is comparable to our hydrogen price, but this price contains a lot of taxes. Natural gas for a private consumer in Germany is 60 cents per cubic meter or 6 cents per kilowatt hour. So the natural gas for a private consumer is cheaper than this hydrogen. Natural gas for the industrial consumer is 25 cents per cubic meter or 2.5 cents per kilowatt hour, much cheaper than our hydrogen produced with an electrolyzer. So conclusion, the hydrogen of the example calculation is cheaper than diesel fuel, but more expensive than natural gas. And however, we should consider the electricity for the electrolyzer cannot be obtained at the exchange price here of the 4 cents, which we had before. Including grid fees and other contributions, the price will be rather 12 cents per kilowatt hour. So the cheapest price for industrial users of electricity in Germany is 12 cents because you have to pay certain taxes and fees. And if we take this into our calculation, you see here the 12 cent instead of the 4 cent, then this fraction here will triple because 12 is 3 times 4. So this fraction here will triple. That means from almost 2 euros to then 6 euros. So it means almost 4 euros more. And this is why we are now at 7 euros per kilogram. And this is 21 cents per kilowatt hour. Even more expensive than diesel fuel. And this shows us that we have to make sure that all the electric energy needs to be freed up from all the fees and taxes. Otherwise, hydrogen production with an electrolyzer won't work. And then the transport cost to the consumer will have to be considered as well. We will come to that in a minute. Let's continue the discussion of the price. So including the transport to the final customer, for example, the gas station, the hydrogen will cost approximately 9 euros per kilogram, which is pretty expensive. And this is, by the way, the price we have now at the few hydrogen fueling stations we have in Germany. But this is still a subsidized price because the frequency, the volume they are selling is so low that this is not a commercial operation. So it is subsidized, but the price now is exactly 9.5 euros per kilogram for the hydrogen. But this price is still acceptable for private cars because a hydrogen car consumes approximately 1 kilogram per 100 kilometers. And that leads to a similar price like a fuel car today. So let's say 9 euros per kilogram, and we need 1 kilogram. That means we have 9 euros for the distance of 100 kilometers. And with the gasoline car, we have 6 liters, but we pay 1.50 euro per liter of fuel. So 6 times 1.5 is also 9 euros. So that means the fuel price is for passenger cars kind of acceptable. However, 9 euros per kilogram would not be acceptable for electricity generation. For example, a combined cycle gas turbine plant using this fuel for this price would achieve electricity generation costs of 47 cents per kilowatt hours. How did I calculate this? I assumed a capex of 800 euro per kilowatt for the power plant, an efficiency of 60%, and 4,000 full load hours, so which are all typical figures for a combined cycle gas turbine plant. That means with this, and do you know what is electricity generation cost by natural gas? It is in the range of 5, 6, maximum 7 cents per kilowatt hours when we run with today's gas prices. You see that this, when we say 7 cents with gas, and this one is 7 times more than. So this is killing. So we cannot use this hydrogen at this price for producing electricity. Nobody would buy this electricity because it is too expensive. So a very important takeaway is the electricity for the electrolyzer has to be exempted from all fees and duties and taxes. Otherwise, the resulting hydrogen would be too expensive for almost all applications. So this is a very important message to politicians which try to deal with the topic of hydrogen. Now let's look at the runtime of an electrolyzer. Let's optimize the runtime, the annual runtime of an electrolyzer. The following 3 slides show the following issues. If we have more full load hours per year, we have less capex per kilogram of hydrogen. The more you utilize the electrolyzer, the cheaper is the capital cost per kilogram of produced hydrogen. And also the cheaper the electricity for the electrolyzer, the cheaper the hydrogen, which is also pretty clear. But now comes a problem. If you have only a few operation hours per year, we can buy electricity at times when it is very cheap. So let's say when you only want to run for 1,000 hours per year, then you can pick those times when the electricity is cheap. But when you want to run the whole year with 8,760 hours, you have to buy all the electricity at all prices, and then the electricity will not be cheap anymore. So we see two opposing trends, and this is a difficult thing. A long runtime per year results in low capex per kilogram of hydrogen, but higher electricity cost, because when you have a long runtime, you also need to buy expensive electricity. That means there shall be an optimum runtime for the minimum hydrogen generation cost, and this we will try to find. First of all, we look at this very simple picture. Here we see the runtime, the full load hours of the year. We start with 1000, and you all know that the year has 8,760 hours, so here the year is over. And the blue curve is at a zero electricity price. That means if the electricity is free of charge, we only have to pay the capital cost and the O&M cost. By the way, we will find here a figure which we had calculated before. The figure was, it's already some slides back, the figure here, this is the capex and this is the opex. Together it was €1.25. €1.25 at 4,000 full load hours. So let's look at 4,000 full load hours, the blue curve. And if you go to the left, we see, if you look carefully, this is €1.25 here. If the electricity would be for free, of course it is not for free. If the electricity would be there for 4 cents per kilowatt hour all over the year, then we have an increase of price, and then the orange curve would be our curve. That means if that would be our price, and we are running 4,000 hours per year, we would produce for €3.12, which we calculated before. Then we said this is eventually not realistic. The cheapest price to get electricity would be with all the taxes and stuff, which we have in Germany, it's 16 cents. And then this would be our hydrogen costs, which would be killingly high. And then there is another problem with this graph. As I said before, we don't have a constant price of the electricity over the year. The price of the electricity is depending on the utilization, and that we will look at the next two slides. So this upper slide shows us the electricity price in the year 2019 of Germany. You see here 0 to 8,760 hours, and this is the price is circling around 4 cents here. Sometimes it is negative. It means when we have much more electricity than we need, then the electricity price is negative, and at some peak demands here, the price is high. But we don't see very much in this picture, so we will sort them now. Imagine these are 8,760 data points, and now we sort them, and so this is a red curve, the lowest one to the left and the highest one to the right. So that means if you go for the approximately 200 hours per year, the electricity price is negative. Then for approximately 100 hours per year, the electricity price is approximately 0. And then it goes up. So after 1,000 hours with a sorted price here, you have 2.5 cents. And then it goes up. And then at the very few hours, the electricity price is really high. You see, it can go up above 10 cents per kilowatt hour. And then this lilac curve here is the average. So what I have to explain this. So what is this going through 0? That's approximately 600 hours per year. That means if I have been buying electricity the 600 cheapest hours per year, then the electricity price in average is 0, because I have bought for 200 hours, I have bought electricity with a negative price. For 100 hours, I have bought it for 0. And then for another 300 hours, I have bought for this price. And the average is 0. If I buy electricity for 1,000 hours per year, the sorted one. So I had some negative price, but I had more positive price. So my average price is 1 cent. And you see that it goes up here at 4,000 hours. It goes above 2.5 cents and so on. And this curve now, this lilac colored curve here, this is now converted from cent per kilowatt hour of electricity into cent per kilogram of hydrogen, because we need to have 48 kilowatt hours of electricity for 1 kilogram of hydrogen. So this is then the orange curve here is this electricity cost, which goes up over time. The blue one is our fixed cost here, the capex and opex. And the sum of the two is the gray one, the hydrogen generation cost. And now we see that there is an optimum somewhere. Here, 5,000, 6,000, 7,000, there it is low, and then it slowly goes up in the end, because in the last hours of the year, we have to pay more for the electricity, and that means the price goes up. So in summary, we can say beyond 4,000 hours per year, the electricity, the hydrogen generation cost is kind of okay. If we run shorter, let's say only 2,000 hours per year, the price is too high because we don't utilize the capital investment. The last topic we look in for the hydrogen generation is the water consumption, because sometimes we read that people say, wow, if everybody wants to produce hydrogen from water, maybe we run into a water shortage. So let's take a look at this. So the water demand for hydrogen generation easily can be calculated by the ratio of atomic weights. So the mass of water divided by the mass of hydrogen is 18 to 2. Because because water is H2O with the atomic mass of O is 16, H2 is 2. So the water molecule has a weight of 18, and the hydrogen H2 molecule has a weight of 2. So the ratio is 18 by 2 or 9 to 1. So due to the pre-treatment of water, desalination, and so on, approximately 10% of the water is lost for the process. So we need, therefore, the mass ratio can be well assumed with the mass of water per mass of hydrogen is approximately 10 to 1. That means for the production of 1 kilogram of hydrogen, we need 10 kilograms of water. A large-scale electrolyzer with a power of 20 megawatt, which we are currently planning to build here in Hamm as a pilot project, produces approximately 400 kilogram of hydrogen per hour. Hence, it will consume 10 times more water. That means 4,000 kilograms or 4,000 liters of water per hour. But water in large quantities, we don't measure it in liters, we measure it in cubic meters. So 4 cubic meters per hour. This is not a lot. So we have the river flowing through our town here, the river called Lippe, has an average flow ratio of 20 cubic meters per hour. Per second, sorry, this is per second. And so please fix this. This is 20 cubic meters per second. And I will fix this. And that means it is 18,000 times more than the electrolyzer will consume. So this is definitely not an issue. And even an electrolyzer of 1 gigawatt would consume 200 cubic meters per hour, and which is only 0.3% of the water of the river. So it is still nothing. Why do I say 1 gigawatt? Because we have a large scale coal-fired power plant here at the river, which has a capacity of approximately 1 gigawatt. And if we would use all the electricity of this large plant, which one is a really big one, to produce hydrogen, then we would consume 200 cubic meters per hour of the river. Look, and the river is having 20 cubic meters per second. That means within 10 seconds, the river could deliver the water which we need for the full hour. So this is definitely not an issue. So bottom line, the water consumption of hydrogen generation is absolutely uncritical. Then let's look into the next topic, hydrogen, transport of hydrogen. Transport of hydrogen is possible by means of pipelines. Pipelines, let's look into this. So pipelines can only be used for gas state, not liquid, because liquid would start to boil, because liquid has to be very cold, as we learned, at 20 Kelvin or minus 250 Celsius. So that means in a pipeline, this liquid hydrogen would start boiling, and then you have a two-phase flow, and this is not possible in pipelines. So you have to transport it in the gas state. And since the 1930s, the industrial area of the Ruhr is connected with the city of Cologne by a hydrogen pipeline. This gas pressure is 25 bars, and the length is more than 100 kilometers, and it is running since 90 years now without major damages. It also even survived the Second World War, where a few bombs hit the Ruhr area, as most of you might know. Then we have the vehicle transport, either in gas state or liquid. In the vehicle transport, liquid transportation is possible, especially with long distance transport. And pipelines are expensive, but they have lower operating cost at a good capacity utilization. That means when you make sure that you have a pipeline and it is operating all day long with a lot of flow, then pipelines are good. But when you operate them only a few hours per day, then they are too expensive and you rather go for trucks. And during the early stages of the hydrogen economy, the transport will mainly happen with trucks, short and medium distances, and rail and ships in the long range. Transport of liquid hydrogen is good because it has a higher density than gas, but we have a high energy demand for liquefaction. So you need to really carefully look at it why you want to go for it. You can transport it easier with less volume, but you spend more energy to make it liquid. And there's another disadvantage. You have the cooling through evaporation. So in a tank, you don't have an active cooling system. You simply let the hydrogen boil, and you have the so-called boil off. So that means the hydrogen which is converted from the liquid state to the gas state cools down the remaining liquid, but you have a continuous loss of mass. And for example, in a passenger car, when you would go for liquid hydrogen, what was done in the 1980s when I worked at the German Aerospace Center, then you have approximately a loss of 1% of the mass per day. That means after 30 days, you have lost 30% of your hydrogen through the boil off. Or you transport it in the gas state, then you need to compress it due to the low density of hydrogen. And all gases needs to be compressed when you transport them. But this is especially true for hydrogen. And then let's look into pipelines, transport of hydrogen compared to natural gas. So the pressure loss equation is that the pressure loss is the density half times the velocity square times the friction coefficient times the length divided by the diameter. The density of natural gas and hydrogen has a ratio of approximately 8:1. And the heating values of natural gas to hydrogen is 3:8. And so that means at the same pressure loss, the pipeline can transport 94% of the energy which could be transported with a natural gas. And because this is very often asked, people think that hydrogen pipelines can transport much less due to the fact that the density is much lower. But you see there are two opposing effects. Because the density is so much lower, you see this pressure loss factor is also lower. That means you can use a higher speed due to this, the square root of 8 times higher speed. And then you transport with the same mass, you transport more energy. And these two effects lead to a factor of 94% of the energy can be transported. However, the flow velocity is square root of 8 times higher. And that means also the power of the compressor will be 2.8 times higher. So for example, the Nord Stream pipeline, very famous pipeline here in Europe, consumes approximately 2.5% of its energy flow for gas compression. At hydrogen, this would be 7%. The alternative is you use a lower velocity. Lower velocity means less compression power, but also less energy flow. So at the same specific energy consumption, the hydrogen pipeline will transport 75% of the energy flow of the respective natural gas pipeline. So it is still acceptable. It is less than this figure, but then now you have the same energy demand. And that means, again, if you would run the Nord Stream pipeline with hydrogen, you would accept that you only transport 3/4 of the energy. Then you would have the same specific energy consumption like today. That means 2.5% of the energy is lost for the pumping. So much to the pipelines. And now let's have a look at the trucks. The typical way to transport it in trucks is a long steel cylinder with 200 bar pressure. You see here a typical photo of a typical truck here. Such a truck carries approximately 600 kilograms of hydrogen, while the mass of the steel cylinders is approximately 22 tons. That means this truck is mainly driving around with steel tanks. 22 tons of steel tanks are carried around and 0.6 tons of hydrogen. Compare, a fuel tank truck transports 25 tons of fuel. That is 41 times more mass than hydrogen and 15 times more energy. That means these typical road tankers with oil in it, they transport 15 times more energy than a truck which brings hydrogen. And then very often I hear, yeah, why don't you double the pressure? But doubling of the pressure would not improve the ratio of hydrogen to steel. Right, with doubling the pressure, the mass of hydrogen would be doubled. But the wall thickness would need to be doubled as well in order to, because you have higher stress on the steel. Hence the tank mass ratio. Then that means the tank mass would double as well, and the steel hydrogen ratio is the same. Even worse, because of the with these high pressures, you cannot consider hydrogen as an ideal gas. So theoretically, with the theoretical equation, the density of hydrogen would be at 200 bar 16.26 kilogram per cubic meter. In reality, it is 15. That means you are already 11% worse. If you go to 350 bar, which is a typical pressure in a truck tank, you are already 18% beyond the theory. And at 700 bar, the typical pressure of a passenger car, you are already 31% beyond the theoretical density. That means going to very high pressures in transport doesn't solve the problem. Then very often I hear, why don't they go into one big tank instead of these 9 pipes here? That is also not an option. So larger tanks are not better than smaller. You see that here in this example, we have 4 tanks, and here we have 1 big tank. Okay, first glance, you say that the diameter is doubled. The area is times 4. But the circumference is doubled, but you also need to double the wall thickness because of the pressure here is making more stress to the wall. That means you need to double the circumference and the thickness. That means, again, you have 4 times more area in the tank. Very good. You have 4 times more hydrogen, but you also have 4 times more steel mass. That means a bigger tank also doesn't help. So then we look into different hydrogen tanks. When selecting the tank's material, the high permeability of hydrogen needs to be considered. At steel, it causes also the hydrogen embrittlement. It means pure steel tanks become brittle over time, and that is not good. After a few years, you need to exchange them. So the glass fiber reinforced plastic or carbon reinforced plastic tanks are better, but they need a lining inside in order to be tight. This is called the liner. So let's look into the typical tank classifications. A Type 1 tank is a normal steel tank, which is shown here, steel wall. Type 5 is like this, but it has a carbon reinforced plastic cover to make it stronger, because when you want to go to very high pressure. Or the type 3, there is all the stability is coming from the carbon reinforced plastic, and you only have a steel or aluminum liner inside because the CRP wouldn't be tight. On the type 4, you have all the stability is coming from the carbon reinforced plastic, and the inside liner is from plastic. And this is, by the way, used nowadays in cars. So this photo shows a typical type 4. You see with the carbon here, the type 4 tank. And here, let's look at some tank examples, type 3, type 4. So the last 4 columns are for the type 4. And these are for trucks with a pressure. You see here is a pressure of 350 bar and 700 bar. This is a typical car tank. So, and here we have the content in kilogram. So the column at the most right, this is a typical car tank. It has a content of almost 5 kilograms. And as we learned before, a passenger car needs approximately 1 kilogram of hydrogen per 100 kilometer. It means this car would have a range of 465 kilometers. So this is a typical tank for a car. And the content here, the gravimetric content is we have here 6% of the mass. It means you see kilogram hydrogen compared to the total kilograms of the tank is 6% here in this case. And the volumetric, the kilogram hydrogen per liter of tank volume is 0.023. And the energy density, that means kilowatt hours per kilogram of tank system, not kilowatt hours per kilogram of hydrogen, but kilowatt hours per kilogram of the full tank, in this case, is 1.48. Compare this to diesel. Diesel has 11.6. Or the volumetric energy density, kilowatt hours per liter of tank system, is 0.77, and diesel has 10. You see, diesel is a lot better than hydrogen. It means the advantage which hydrogen has, that it is very light, is overcompensated by the high mass of the tank systems. This should not be forgotten, because people sometimes look at the properties and they say, oh, fantastic, hydrogen has 3 times more energy content than fuel. But you have to consider that fuel you can put into a very cheap tin vessel, and then you have it contained. And with hydrogen, you need to have this 700 bar pressure. And you see that only here, this line, 6% of the weight of such a system, 6% is hydrogen and 94% is tank. Summary of transport. Pipelines. Only pressurized gas, no liquid hydrogen. High investment, low operation cost. Only economic at high utilization. You can mix hydrogen into natural gas pipelines. So 5 to 20% volume share is definitely possible. Then come to transport in vessels. Liquid hydrogen has a high density, but high energy demand for liquefaction. Pressure tanks are available in the following pressure vessels, pressure levels 200, 350, and 700 bar. So above 200 bar, you have the tank type of 3 or 4. In the passenger cars, you have the type 4. Relatively new is the binding of hydrogen in organic carrier media. There's an advantage. It has a higher energy density. The disadvantage is you have energy demand for binding it into the organic carrier. Bottom line, a truck only transports 1 ton of hydrogen instead of 25 tons of oil. That is 25 times less mass and 9 times less energy than with a road tanker, which brings gasoline or diesel or heating oil. So transport costs of hydrogen will be significantly higher than with oil. This should be considered in the range of 10 times higher per energy content. So summary of transport. Here we see here the transport costs in dollars per kilogram which you transport. Here you have the mass flow in tons per day. And here you have the transport distance. So when you have small quantities like 10 tons per day or 20 tons per day for a long distance, then we see we are in the range of more than $3 per kilogram. When the quantities get bigger, then we can, let's look at the abbreviations. P is pipeline. Here is the regime where the pipeline is working. Here is the gas state, and here is the liquid state. So let's look at an example. Let's say we have a pipeline for 500 kilometers at a very high quantity, 100 tons per day, 500 kilometers. So we are here at approximately $1.50. Then we have a pipeline with a very high transport rate, and then we have only 100 kilometers. Then we have transport cost below $1. But with all these very small quantities here, we have, even with short distances, we are easily in the range of $2 per kilogram. And this we have to face with supplying gas stations. You know, the gas stations, they don't have so high quantities. That means they need to be bought with a gas state tank, road tanker, and then we are facing transport costs from the production to the gas station in this area, in this range, and which is quite a lot. Remember that the production of the hydrogen could be as cheap as €3 per kilogram. Let's say euro and dollar is almost the same. Then comes $2 or €2 on top of it for the transportation. Next topic is the utilization of hydrogen. And one is the reconversion into electricity. You can do it centrally in a combined cycle gas turbine plant. Efficiency is above 60%. Advantage is it is established and cheap. You can do it decentralized in a fuel cell. Efficiency is the same. Advantage is you are closer to the customer. And this is a cornerstone of the energy transition. So the reconverted electricity will be needed in times without wind and solar energy. That means beyond a certain share of renewables, you can't live without hydrogen. So nowadays in Germany, we make almost 50% of our electricity from renewables. So far, it is working without hydrogen storage because when there is no sun and no wind, we burn gas or coal. But when we want to go to 80 or 90% share, then we have to reduce the gas and coal to a minimum. Or even if we want to go what we want to do in the year 2045 in Germany to zero carbon electricity production, then we need to produce all the electricity, even if there is no wind and no sun, with renewable energies. And this can only be done with hydrogen, which has been produced from renewable energies. And the hydrogen demand for this long time storage will be higher than in the transport sector in the long run, just to make this clear. Then the utilization in the industrial processes. Steel production, for example, hydrogen can be used as a reductive instead of coke. It has been shown in pilot plants, and there are plans to use this on a large scale. Then the production of fertilizers need hydrogen already today. And the hydrogen consumption in Germany is today approximately 19 billion normal cubic meters. And this has an energy content of 57 terawatt hours. If you would produce this hydrogen with electrolyzers at an efficiency of 70%, you would need, of course, more than this amount. You would need 81 terawatt hours of electricity consumption for producing the hydrogen, which is already needed today in Germany. And this would be 13% of Germany's total electricity consumption, which you need for this. That means there is an immediate demand for this amount of hydrogen, which consumes this amount of energy. And that means as long as this is not satisfied, you actually don't really need to look for other consumers, because these consumers are eagerly waiting for the green hydrogen. So yeah, very important. I have not talked about this before. We only talked about the reconversion into electricity and so on. That means very important here. Even when the industrial utilization is only mentioned on one slide in this presentation, it will be the first one which will work without subsidies, because here the hydrogen is definitely needed and there is no alternative. But now let's look into the utilization in passenger cars. A passenger car can be hydrogen powered in two ways: an electric motor with electricity from a hydrogen fuel cell, which is abbreviated here with FC, fuel cell, and then a combustion engine with hydrogen as a fuel. The technology too has been successfully tested in the 1980s when I worked at the DLR. This was a BMW, which we had at our institute. Here was a refuel station, and it was fueled with a liquid hydrogen. It had a liquid hydrogen tank, and it didn't have a fuel cell. It had a combustion engine, which was running on hydrogen. It was running pretty well, actually. So then technology one only became feasible with the progress in fuel cell since the end of the 1990s. So in the 1980s, such a fuel cell was not available, but since the end of the 90s, such fuel cells are available, and modern hydrogen cars like the Toyota Mirai, for example, they convert hydrogen into electricity with the fuel cell. The advantages of a fuel cell against a hydrogen combustion engine are the following: better efficiency, 60% efficiency instead of 30 to 50% in a combustion engine. And you can have the recuperation of energy from braking. So when you brake with such a car, the electric motor switches into the generator modus and is producing electricity, which is fed back into the battery. That means when braking, you don't lose the energy. You get it back and can put it into the energy, into the battery. And with the combustion, you wouldn't be able to do that. Typical consumption of hydrogen cars is, in a modern fuel cell passenger car, 1 kilogram of hydrogen per 100 kilometer. And in a combustion engine, it is between 1.5 and 2 kilogram per 100 kilometers. So significantly worse what we did here 30 years ago. But it was possible already 30 years ago to drive a car with hydrogen. So the rule of thumb for primary energy consumption of a hydrogen-driven car. Let's look into the numbers very quickly. So the energy demand of a typical passenger car, electric, is 20 kilowatt hours for 100 kilometers. So the users of electric cars know this. That means for driving 100 kilometers, you spend an electricity of 20 kilowatt hours. The lower heating value of hydrogen is 33 kilowatt hours, but you don't get it converted into electricity one-to-one. You only convert 60%, and 60% of 33 is 20. And this is why you spend 1 kilogram of hydrogen on 100 kilometers. Once more, you spend 1 kilogram. The energy content of that kilogram is 33 kilowatt hours, but you only convert 60% into electricity. That means here you have the 20 kilowatt hours of electricity, which also a battery electric vehicle would need. Now, let's look into the primary electricity consumption. A typical electrolyzer with an efficiency of 66% needs 50 kilowatt hours of electricity to produce 1 kilogram of hydrogen. That means in the end, the hydrogen car is consuming an electricity of 50 kilowatt hours. Again, we have 50 kilowatt hours of electricity. We send it through an electrolyzer. We produce 1 kilogram of hydrogen. This 1 kilogram of hydrogen we put into the car. The car converts it into electricity and gets 20 out of it. So in the end, while an electric car is running 100 kilometers with 20 kilowatt hours, the hydrogen car is needing 2.5 times more, 2.5 times more electricity than a battery electric vehicle. This is important to note. And by the way, battery electric vehicles and hydrogen cars are not the only vehicles which drive without CO2 emissions. Cars with gas-fired combustion engine can be run with biomethane, and then they are also CO2 free. And the production of biomethane in Germany is not big enough to run all cars in Germany with it, but there is a significant potential which should be utilized. This is a low-hanging fruit which should be picked first. Utilization in commercial vehicles, urban buses, trucks, and special vehicles like garbage trucks, street cleaners, and so on. Advantage of hydrogen fuel cell against battery electric vehicle: you have a larger range with hydrogen, you have faster charging, and the hydrogen tank has less weight than the battery. The disadvantage of the hydrogen fuel cell vehicle against the battery electric vehicle is higher primary energy consumption, 2.5 times higher due to the round trip efficiency. Higher fuel cost, because hydrogen is more expensive per kilowatt hour than direct electricity because of the losses. So let's look at the example of an electricity or hydrogen consumption of an urban bus. The electric bus needs 160 kilowatt hours for 100 kilometers. The hydrogen fuel cell needs 8 kilograms. But the primary electricity consumption of this bus, because remember, we spent 50 kilowatt hours to produce 1 kilogram of hydrogen, and 50 times 8 is 400. That means the hydrogen bus is in the end consuming 400 kilowatt hours, while the electric bus is only consuming 160. Again, we have this factor of 2.5 here. The development trend, and I think this is a very clever one, is that we have a hybrid system with battery and a fuel cell as a range extender abbreviated with REX. This is also possible with passenger cars. We will see that on the next picture. So the typical fuel cell bus looks like this. It has a hydrogen tank, a fuel cell, and this fuel cell produces electricity and it's driving the electric motor. And still you have a little battery because for the peaks, when the bus is accelerating or driving up a hill, the fuel cell doesn't have enough power for this. So for a few minutes, there is a battery which will power the electric motor here. And anyway, the battery needs to be here for the recuperation. When the bus is braking, the motor produces electricity, which goes back to the battery. So this is why also in a fuel cell mode, you have a battery. But now we come to the hybrid mode with the fuel cell and the REX. Here you have a smaller, you see this compared to the left side, a smaller hydrogen tank, a smaller fuel cell, but a big battery. So that means we can run approximately half of the daily route the bus can run with a battery. That means it is charged during nighttime with cheap electricity. And then after half of the day, the battery is empty. And then the hydrogen tank starts and we run from the fuel cell, produce electricity, and then we run on hydrogen. Let's look at examples here. The fuel cell bus has a battery of 30 kilowatt hours. This is a small buffer battery, but has 40 kilograms of hydrogen, and the fuel cell has a capacity of 100 kilowatt. The hybrid system has a big battery, which is good for 150 kilometers. It has a smaller hydrogen tank of only 15 kilograms and a smaller fuel cell. And here are the figures. So the battery, and here's the fuel cell with REX, like we saw here, and we have the pure electric version here. The pure electric version has a battery of 480 kilowatt hours. And so the range on battery here is 30 kilometers, the pure electric bus. The fuel cell would run on this little battery only 20 kilometers, and the fuel cell with REX has a battery for 160 kilometers. Then we see how long can we run on hydrogen. The pure electric bus, not at all. The pure fuel cell bus runs 500 kilometers on hydrogen, and the REX one has 250. So the total ranges are as follows. The pure electric bus has 300 kilometers, the hydrogen 520, and the one with the REX 410. Then we have the cost of the battery. Batteries are very expensive, so this is killing the battery bus. Then you have the cost of the fuel cell and the hydrogen tank, which is most expensive here at the fuel cell version. And the total cost of the powertrain, that means including battery and the hydrogen system. So the most expensive bus is the battery bus. The cheapest one is the hydrogen bus, and the medium is a fuel cell with REX. But now let's look at the energy cost of 250 kilometers. 250 kilometers is a typical daily range of such a bus. The electric bus needs 20 euros per day. The fuel cell bus needs 3 times as much, and the REX has some bit in between. And now for a full year of 200 working days, the costs are the fuel costs are as follows: 12,000 for the electric bus and 3 times more for the hydrogen bus. And you can see after 2 years, the hydrogen bus is already more expensive than the battery electric vehicle. But the cheapest one on the long run is the hybrid one, because it's much cheaper than the pure battery, and the energy costs are closer to the battery than to the hydrogen. So what have been the assumptions here? The battery costs are 200 euros per kilowatt hour. The fuel cell is 300 euro per kilowatt, pretty optimistic. The hydrogen tank is 1000 euro per 5 kilogram. The hydrogen cost is like today 9 euros per kilogram, and the electricity is 15 cents. Like large consumers get it, and bus companies would be large consumers. And the consumptions is for the electric bus, as we showed on the last page, 160 kilowatt hours electricity or 8 kilograms of hydrogen. By the way, the most cost effective would be when the REX is a combustion engine running on biomethane. This is much, much cheaper than the fuel cell range extender. Then we continue the utilization and the intermixture. We can just, when we produce hydrogen, which we have to do very soon, because when we continue to build wind and solar in Germany, we will have surplus energy for zero price, and we have to produce hydrogen with this in order to create a source of income for those power plants. Otherwise, they are not commercially viable. So we need to produce hydrogen, and we need to do something with it. And so we can simply mix it with the natural gas in the pipeline. So hydrogen can be blended with natural gas in the gas network. The limit is beyond which percentage of hydrogen the appliances need to be modified. So pretty tolerant are gas heating systems and ovens. They tolerate easily 20% volume percent of hydrogen. Less tolerant are gas turbines. They can tolerate approximately 5% without modifications. And of course, the driver in the system is the most sensible appliance in the network. So it means when we have a pipeline which is feeding households with gas heaters and gas turbines, we can only blend in so much hydrogen as the most sensible appliance can stand. So let's go for the 5%, which is 1.5% energy. The German gas grid transports approximately 1,000 terawatt hours of energy every year. And this 1.5% of this is 15 terawatt hours. That means we can easily put 15 terawatt hours of hydrogen into the gas network. And if we produce this amount of hydrogen with an electrolyzer of 70%, we would spend 21 terawatt hours of electric energy for this. This is approximately 3.5% of the total electricity consumption of Germany. And this would be done with a utilization of surplus electricity of wind and water. And if we want to produce those, want to consume these 21 terawatt hours for the electrolyzers in 4,000 full load hours, then we would need electrolyzers of 5 gigawatt. I think this is enough to do for us for the next decade. By the end of this decade, we might have 5 gigawatt capacity of electrolyzers, And what can we do with this? If nobody wants it, we can simply mix it into the natural gas network and nobody will complain. Yeah, as I said before, so that much surplus could immediately be used to produce hydrogen and feed it into the gas grid instead of shutting down wind farms on windy days, which is unfortunately happening more and more. Last topic is the storage. Storage of hydrogen. Here, this is in NASA in Cape Canaveral for the moon rocket. Here, they had a liquid hydrogen storage, of course. So it has the highest energy density. It consumes 30% of its energy content to make it liquid. It must be kept at minus 243 degrees. Cooling through boil-off, that means you lose hydrogen over the time. Therefore, it's not an option for long-term storage. That means only for transport or in fuel tanks of vehicles where it is used within a few days. Then the gas pressure reservoir is mobile. You can use it mobile in carbon or steel tanks, as we saw it before with the trucks. Stationary, this is a typical tank here. Steel tanks of 200 bars is the level there. And centralized large quantities then in subsurface gas storage caverns. That means you take reservoirs, which you call caverns in this case, where natural gas was before. And in Germany and the Netherlands, we have a lot of those which are empty since the production has finished, has run out. And these caverns are available to put hydrogen into them as a seasonal storage. So many exhausted natural gas caverns are in Germany. That means a seasonal storage is possible. So, and how does all this fit together? The next few slides, we will see how the individual components of the future energy system will all interlock. Because the sectors, energy generation, transport, and heat use, all have to be interlinked. This is also referred to as sector coupling. So let's look at an example. This was an example of a sunny period. This is the period from 15th of July to the 26th of July in 2018. It was a very sunny summer. And here we see the different, here you see here the power in gigawatts, 50 gigawatt, 75 gigawatt, 100 gigawatt. And as I told you before, the average power consumption in Germany is 70 gigawatt. So this 70 gigawatt is somewhere here. This is the average power consumption of Germany. How is it produced? So the green one is biomass. It's a base load. It's running through. This blue one here, the light blue one, is hydropower. It's running through. Then this blue one is wind onshore. This dark blue one is wind offshore. The yellow one is solar. And in summer, you see every day you have a solar peak. And this gray one is conventional electricity, fossil and nuclear. And this all can be looked up here. We will go there in a second. This website, Agora Energiewende, it is a very useful thing. I think very few countries have such a feature. We will go to this website in a second, but now let's look at the very windy period. This was in March 2019. You see here 4 days. You can even always count these yellow peaks here. This is solar, but this is March. You see 11th of March, 12th of March, 13th. So we have here 4 days. And in March, the sun contribution is not so big as in summer, but the wind is big. You see, this is onshore wind and this is offshore wind. And you see that the wind is even more than the sunshine was in summer. That means the gray areas here of fossil production is even lower in springtime than it was in the summer. So, and now let's have I hope this works for you, that you will see that during the presentation. I hope this can be seen. I'll make it very quickly for the case that you don't see it. So this is here, and here this is the Agora. Energiewende, and here you can now put dates. You can say, I want to see from 3rd of May this year until the end of the week, the Sunday. And then you make display. It's also in English available. And then we see now 1 week, 1, 2, 3, 4, 5, 6, 7 days from 3rd of May until the 9th of May. So I hope this was seeable. And now we are back to the PowerPoint. Yeah. And why did I show you this? We will see that the next slide. So, okay, so I forgot to transfer this into English. I'm sorry. This is the sector coupling for traffic. Battery-powered electric vehicles provide the opportunity to power the transportation sector with renewable. Especially for vehicle owners with PV systems on the roof of their house, renewable shares of over 80% of the charging current are often achieved in the annual average. The REN fraction is also very high, especially in summer, for those battery electric vehicles that are charged during the day at work or while shopping in parking garage due to the high PV midday peak. We just saw the graph before. In summer, the power in the grid is to a large extent solar power. That means it is very welcome if this is utilized. That means even if you don't have a PV system at home, when you charge while shopping or at your work, you are also charging solar energy to a large extent, and every year it will be more. So the additional electricity demand at midday makes good use of the midday peak and eliminates the need for expensive intermediate storage for later use. And now, this is why I showed you the Agora meter before. This is 1 day, you see, from 0 to 24 hours. And here we have the power, the average power of 70 gigawatt in Germany. And the blue one is hydropower and biomass, which is running through. This is a windy day. See, the wind was almost 40 gigawatt here and then decreases a little bit over the daytime. And it was a sunny day. If you look at the height of this solar bubble here, it is also something like 40 gigawatt of solar. This dotted line here is the electricity demand of Germany, and the gray one is the fossil. So this is a measured date, a pretty sunny and pretty windy day. With the installation rate, because it was recorded in 2019, with 48 gigawatt solar installed and 60 gigawatt wind installed. There was no surplus. The average power was a typical day with 70, you see 70 here, 70 gigawatt average demand. The energy demand of the day was 1,680. The fossil generation, here the gray one, was 442, which is a percentage of 26% of the demand. So this is the situation today. And now we will double PV. So let's say in a few years, we will have managed to double the PV capacity. That means this yellow bubble, which we had here before, will be double as high. And then you see we have a surplus here because this is a dotted line, this is the demand line. And this above here is the surplus. So we have now a surplus of 216 gigawatt hours during the daytime. So by comparison, Germany's pumped storage power plants can store 33 gigawatt hours. So they would not be able to absorb this energy. What can we do with it? So the pumped storage is not the solution. Question: how much electricity would need all German cars if all 4 million cars were electric? So the daily mileage of the German driver is 40 kilometers a day. The consumption of a car, electric car, is 20 kilowatt hours per 100 kilometers for Tesla, a bigger one. So smaller cars like the Renault Zoe also take only 15, but let's be pessimistic here, 20. And then we have 40 million cars in Germany, and then we multiply it simply up. 40 million cars, 40 kilometers per car, and this consumption, that means we need to charge all cars each day. We would need 320 gigawatt hours. So this is actually more than the surplus. The surplus on this day is only 216. We would need 320. But at least we can charge 2/3 of this surplus can be used to charge the entire car fleet of Germany. And now we also want to increase the wind power. So we go up with the wind power. So now we also double the wind capacity. Compared to the original picture now, the wind is doubled. You see here the demand line. That means now we are, even in the morning hours, we have more electricity than we need, because this is the demand line. Here we are. Then in the daytime we have a big plus, and only in the afternoon there is a little gray area. So the surplus on this day is 745 gigawatt hours. And the fossil generation remaining is only this 2.5%. So now there is a surplus of 645 gigawatt hours. This can provide the charging current of the 320 gigawatt hours for all the German cars, which we have calculated before. And then there is still a surplus remaining of 325 gigawatt hours. And this can now be used for heating, power to heat, or for hydrogen generation, for the power to gas. The fossil power generation is only 2.5, and this can be then used, can also be realized with hydrogen. So, but you have to consider, the example shows a sunny and windy day. Even with the PV installed, a high installed PV and wind capacities, there will be often less PV and wind power, because this is for pretty good wind and sunny conditions. Even with this high installation rate, you might have on some days much less than this. And then the gas-fired power plants have to step in. In the coming years, they would have to step in with natural gas, but on the long term, they can run on hydrogen, which has been produced here from power to gas. And you see, this is how the whole system starts making sense. The last slide before the conclusion is the heat utilization as energy storage. Typically, heat generation from electricity is considered inefficient, because the electricity has been generated from heat with efficiencies between 45% in a coal-fired plant and 60% in a gas-fired plant. But now let's compare the electricity as a heat source with natural gas. So let's assume there is a very windy and sunny day. We have surplus electricity. There is a house owner who has a gas-fired heating and an electric heating in parallel. So because the electricity is cheap on this day, because there is a surplus, if 1 kilowatt hour of electricity in times of electricity surplus is used for heating in a house with the gas heating, this 1 kilowatt hour replaces 1 kilowatt hour of natural gas. From the saved 1 kilowatt hour of natural gas, later, let's say the next day when there will be a lack of renewable energy, then you need to burn the gas, and then this saved 1 kilowatt hour of natural gas will produce 0.6 kilowatt hours of electricity. So with a power plant efficiency of 60%, which is standard today, that means in the end, by using this heat for power to heat, we have a round trip efficiency of 60%, because indirectly we have saved 1 kilowatt hour of gas, which can be converted into 0.6 kilowatt hours of electricity. If the 1 kilowatt hour of electricity were instead stored with hydrogen and then converted back to electricity, the power to gas, we would only get back 0.4 kilowatt hours, because the round trip efficiency, as we saw before, is 40%. That means burning the excess electricity is more effective than storing it in hydrogen in a daily time frame. Long term is of course difficult. The heat storage is mostly for a day or maybe 2 or 3. And the associated infrastructure, what we need here, water tank and heating rod, is very cheap and pretty much available in houses. And now we come to the conclusion. Hydrogen is a feedstock and an energy storage. Energy storage, electricity, hydrogen, and back to electricity. Advantages. Hydrogen is the ideal and only feasible seasonal energy storage. Hydrogen has a higher energy density than electricity stored in batteries, so it is well suited for powering heavy vehicles. Disadvantages. The round-trip efficiency is less than 40%. Transportation of hydrogen is more expensive than the one of oil or gas. Remember that the truck is only bringing 10% of the energy compared to an oil road tanker. Conclusion: hydrogen is an important element of the energy transition for the sector coupling. The first big market for green hydrogen will be the utilization as a feedstock for the chemical industry, where hydrogen is already used today. Where hydrogen will prevail over direct electricity use remains to be seen. That will be determined by the market with the following steps. So let's say we have a lot of renewable electricity. There is an electricity surplus. That means we have a lot of cheap electricity for electrolyzers. If there are many hydrogen users, because there is cheap hydrogen in the market, electrolyzers will need more than only the surplus electricity, because they have to run many hours, also in those hours where it's not a surplus, but where the electricity needs to be specially generated for them. That means then the hydrogen price will rise again and the number of hydrogen users will go down again. That means this is the balance, the last two sentences here. This is the balance which will show whether the direct use of electricity or the stored use via hydrogen will be more. Of course, both will have their place, but how the percentage will be in the end, this will be shown in the future. And so we have to be very flexible and react to the signals which the market will send to us. The last slide shows you here literature selection. This is unfortunately all in German language. So if you really want to become a hydrogen expert, I think German is a useful language, but there's also, of course, a lot of English-speaking literature available. And believe it or not, after less than 2 hours, I'm finished with the lecture. I thank you very much, and I stop the recording here. Thanks for listening. Bye-bye.